Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone, and welcome to this new episode of GaN Talk podcast. Today we will talk about AI infrastructure. As you know, we have posted our latest blog talking about NVIDIA MGX architectures, where we have highlighted our EPC 91123 board. As you know, AI infrastructure are becoming important, increasingly power hungry, and efficient power conversion is becoming just as important as compute performance itself. Today, we are exploring one of the most critical technologies powering the AI revolution, gallium nitride, or GaN. And our special guest is Alex Lido, CEO of EPC. Hi, Alex. Welcome aboard. How are you doing?
Hi, Maurizio.
Thank you for being here. Thanks a lot. So, today we will talk. So, I have a couple of questions to share with you. We'll talk in terms of AI infrastructure, our collaboration with NVIDIA MGX architecture. So my first question, silicon has dominated the power electronics space for decades. What has changed in the AI era that makes GaN an alternative, a choice?
So, a few things. First of all, for several years, it's been true that if you want to improve your power conversion efficiency, use GaN. But with the advent of these very high density AI servers, power has become the limitation. They can't consume more power unless they can distribute it more efficiently. And so that has not only made people rethink the architecture, but also rethink what types of components they use that might make it more efficient. Now, in the last year, EPC introduced its 7th generation of GaN technology that extends our performance lead all the way down to 0 volts, which means that at any of the nodes along the way from 800 volts all the way down to point of load, the most efficient solution is using EPC's GaN. So if that limits your performance of your system, you have to use GaN.
So when comparing GaN to traditional silicon MOSFET, tell us what are the key technical advantages that EPC is offers for AI infrastructure in switch frequency, efficiency, power density, and thermal performance?
So our new generation 7 devices are about 3 to 4 times lower in capacitance, switching capacitance, than any MOSFET out there. They're also, 2 to 3 times smaller in size. So you can pack them closer together, and it takes less energy to switch them. Now, switching energy, it adds to heat or thermal dissipation, as does the on resistance of a part. Well, if our parts are much smaller than a silicon die for the same on resistance, you can also make them the same size as the silicon die for much lower on resistance. So you can lower the switching losses, you can lower the conduction losses. Also, our packaging is dual-sided cooled, and you have direct access to the device on the back surface. So thermally, it's more efficient than the MOSFETs. So you have thermal conduction efficiency, you have switching efficiency, you have conduction efficiency. What's not to like in that?
So, as I mentioned at the beginning in our recent blog post, we covered the role of EPC GaN solutions in NVIDIA MGX and 800-volt DC-based systems. So, EPC 91123 demonstration board, it has drawn attention for its very high efficiency conversion of 800-volt DC to 12.5-volt DC. So, what does this platform teach us from engineering perspective for the future of AI power architectures?
So this 800 volt to 12 volt DC to DC converter uses something called an ISOP, or inputs in series, outputs in parallel architecture. It's 8-stage. So each stage takes 100 volts. And you take 8 of them, that goes all the way up to 100 volts. And it really shows how voltage sharing, which is extremely simple with ISOP architecture, voltage sharing allows you to use low voltage transistors, low voltage GaN devices, which when they're added up, they're much lower on resistance than if you just used high voltage devices, silicon carbide, silicon, or even high voltage GaN. So you actually save quite a bit on the conduction losses for the same amount of semiconductor, but also you save a lot of switching losses. Now, you can also go to much higher frequencies. This 91123 runs at a megahertz, and that allows the board to have very thin transformers. The entire thickness of the board is 8 millimeters, and that means that it can fit right on that server card and allow plenty of space for a cooling plate to go over it. That is, I'd say, central to the new architectures in the Vera Rubin servers.
So there are several design approaches possible for the next generation AI power system: 800 volt to 48 volt, 800 volt to 12, 800 volt to 6 conversion. So as we mentioned in the blog post that you can find on epc-ceo.com. So talking about these different approaches, what are the practical trade-offs of these architectures from an EPC perspective?
So there are many trade-offs. I think in the case of 800 to 48 volt, that allows the least amount of disruption to the current architecture. The current architecture today delivers 48 volts to the server card and then takes 48 volts down through various stages to point of load. So probably it's the simplest, lowest risk first implementation. The minute you go to 800 to 12, it makes the most sense to bring that 800 volts right onto the server card. So the connectors no longer have to conduct hundreds of amperes, but they do have to connect hundreds of volts. So there's, I'll say new engineering associated with that. Now the 12 volts has to be distributed around the board. So rather than distributing at 48 volts, you're distributing at 12. So there are more conduction losses. What this means is hopefully the 800 to 12 volt DC-DC converter is small enough that maybe you can have a few of them on that board to minimize the distances that the current has to conduct at 12 volts. The minute you get to 800 to 6, again, that's on the server card. So you can imagine conducting hundreds and hundreds of amperes at 6 volts could be very inefficient. It could require a lot of copper and have a lot of conduction loss. And so you need to have these things very carefully positioned close to the consuming elements, in this case, mostly the GPU. But the 806 volts allows you potentially to skip an entire stage, because from 6 volts, you can go directly to point of load and eliminate that intermediate, IVR stage that is there today between the GPU and, say, 2 volts or 1 volt or 3.3 volts. So they all have trade-offs. There's engineering associated with all of them. And I think we will see an evolution from 48 to 12 to 6 over the next few years.
So, in practice, as voltage go lower and current demands increasing around the GPUs, so it will be important devices, EPC, our devices like 2370, EPC 2370, these will be becoming more and more important. So they are changing, the equation for high current point of load conversion. So what do you think?
Yeah, I think that the EPC 2370 is a 15 volt device, and it's a game changer. It has a typical on resistance of 280 micro ohms. That's almost the same as copper. It comes in a tiny 3.3 by 3.3 QFN package, and it's rated at 18 volts. Now, GaN has an advantage over silicon in that you can have overshoot in GaN. So the 18 volts actually has a 22 volt overshoot capability. So really, you get this incredible GaN performance that can effectively eliminate a 25 volt MOSFET in that socket, which has 3, 4, 5 times the same on resistance in the same size package, and has a lot more switching capacitance as well. So this is a real game changer for 6 volt out in particular, for 6 volt out or 6 volt in.
So physical space around the GPUs is very small, very limited. So especially in what the NVIDIA company would call NVLink space, NVLink radius. So why, in terms of why does the size and thickness of the converter matter in these settings? So, and how EPC GaN technology would overcome this issue?
So it matters in two different ways. One is the height of the system is very limited. With the new Vera Rubin, they're going to 27 millimeter centers for the server cards, which really, they all have to be liquid cooled. So you have very, very limited space for devices. And so number one, there's a height limitation. Number two, you're conducting thousands of amperes to get to these new GPUs, 2,000, 3,000 amperes for a single Vera Rubin GPU. So the proximity to the GPU is very important because the resistance or load line resistance can be very significant with thousands of amperes. So you want to have these devices as close as possible, and you want to have them as thin as possible so they can be cooled with the cooling plate and they don't have a lot of load line resistance getting to the GPU.
So we have seen many topics in this podcast. Thank you, Alex, for sharing. The my last question to conclude. So if you had to put money on this dominant architecture for AI, a specific AI dominant architecture or AI data centers 5 years from now, for example. So do you expect the industry to cover one specific topology, or will multiple power conversion approaches coexist? So depending on the workload and requirement that AI infrastructure will require.
I think it's a little bit hard to say at this point, but if I were to put money on it, or say steer R&D towards it, I would say that the 800 to 6 volt conversion will eventually be the best solution. And it will also allow for a 6 volt conversion directly to the GPU. So you eliminate an entire stage or even 2 stages in the conversion process, allowing you to do that whole thing more efficiently. Today, you can do 800 to 6 volt conversion with 75% efficiency, and you can do 6 volt to 0.6 volt at 90, 91% efficiency. So you have an overall system efficiency of about 90%, getting all the way down from 800 volts to the GPU. And I think that is going to win in the end.
Thank you, Alex. Thanks a lot. It has been a pleasure talking with you. See you next, and stay in touch to EPC website for more news and blog articles. Thank you, Alex.
Thanks, Maurizio.